Hello everyone, I'm Jianwen Zhou from Max Planck Institute for Radio Astronomy. Firstly, the physical picture. Galaxies are cell factories in the universe. A galaxy can include multiple molecular clouds. Those clouds are localized star-forming regions within the galaxy. A molecular cloud can include multiple clumps. Those clumps are local dense gas structures within the cloud, and they are the progenitors of star clusters. Uh, and the real star-forming sites within the molecular cloud. Furthermore, a clump can include multiple dense cores. Those dense cores are the real progenitors of stars. So for star formation, we have these hierarchical structures from galaxy to molecular cloud, to clump, to dense core. So here is the molecular cloud complex in the Milky Way. This cloud includes hundreds of clumps. And this is the middle infrared image of this region from space. So if we put this molecular cloud in a nearby galaxy, such as NGC 628, the distance is around 10 megaparsec. So to some extent, it's equivalent to smooth this image hundreds of times. So we got this one, and all details disappear. And here are the real images from observations for the NGC 628. This is the ARMA CO, and then this is the middle infrared from GWST. For nearby galaxies, although we have used the most advanced facilities such as ARMA and GWST, but generally we can only resolve on the cloud scale. However, for those large scale phenomena of star formation on the cloud scale, to really understand the potential physical mechanisms, we need to characterize the physics on the clump scale. To actually, for the star formation on the cloud scale, uh, the star formation on the cloud scale is the integrated outcome of star formation on the clump scale. And so we start from the star formation on the clump scale. Especially, we study the relation between the clump and the embedded star cluster formed in the clump. And here we focus on those clumps with H2 regions. These clumps represent the final stage of star formation in the clump and the first stage of those gas-free star clusters. So here we associate those clump with H2 regions with radio sources. So a clump can include several radio sources, and we focus on the most powerful one, which represents the most massive star formed in the clump. And then from Lyman continuum flux, we can estimate the stellar luminosity and mass. And then based on the initial mass function, we can derive a theoretical relation between the cluster mass and the mass of the most massive star in the cluster. And then we can calculate the cluster mass and further calculate the star formation efficiency of the clump. And so here we can see a clear anti-correlation between the clump mass and the star formation efficiency, with a median value around 0.3. And then the next step is from clump to cloud. Currently, only 4 molecular clouds in the Milky Way and several very near extragalactic systems we can resolve on the clump scale, generally 1 parsec or sub-parsec. And here I show the relations between the cloud mass and the total clump mass within the cloud and the star formation rate of the cloud. And yeah, this is the cloud in the Milky Way. But for the clouds in nearby galaxies, we only have some physical parameters of the cloud. We know nothing about the clumps within the cloud. However, based on the observation in the Milky Way, uh, according to the cloud mass, we can estimate the total clump mass within the cloud, and then assume this clump mass function of the cloud. Here we use the formalism. This formalism is from the embedded star cluster mass function because the clumps are the progenitors of embedded star clusters. So here we assume this inheritance between these two, and then through this the total clump mass and the clump mass function, we can generate the clump population for a cloud. However, currently these clumps are only point the currently existing clumps. Actually, a cloud, apart from clumps, a cloud can also include stellar populations, and those stellar populations are also from the past clumps. And so we also need to estimate the stellar mass of the cloud and transfer the stellar mass to the clump mass through this star formation efficiency. And then combine with the currently existing clumps, we can construct the initial clump population for this cloud. And then how to distinguish the different components. And then we need to model the star formation history of this cloud. It's equivalent to distribute the age to each clump. And then according to the age, the oldest clumps now evolved into those exposed stellar populations. And those embedded stellar populations have the middle ages. And the youngest clumps are the currently existing clumps. So we have this, generally we have these three components. And then we have this workflow from the cloud mass, the stellar mass, and the currently existing clump mass, and combine with the clump mass function, we can generate the initial clump population for this cloud. And then we model the star formation history of the cloud and distribute the age to each clump. And then we sort out the clumps uh, uh, have the in the middle ages, which represent the embedded stellar populations, and then divide the duration time of embedded phase. We can predict the star formation rate of the cloud. And this theoretical star formation rate can be compared with the star formation rate derived from middle infrared emission in observation. Okay, and then this is the results from the model. In the model, if we consider the stellar populations, so we can say the model can fit those high mass clouds. Because the reason is, actually, now we do not know the relation between the stellar mass and the cloud mass across this mass range. Actually, currently, this relation is only derived from some massive clouds in nearby galaxies. Because in some nearby galaxies, it's easy to associate the stellar population and the molecular clouds. So yeah, naturally, yeah, this relation is only feasible, useful to those high mass clouds. And then for this blue, this one here, we do not consider stellar population because for those low mass clouds, it's expected that they do not consider a significant fraction of stellar populations. If not, yeah, the stellar population will destroy these clouds. So now we have these two extremes. And for the clouds in the middle, they should be between these two extremes. So here we use this linear weighting function to link the high mass end and low mass end, and to realize a smooth transition. So now we can say the model can fit the observation. Okay, and finally, it's from the Milky Way to nearby galaxies. And those orange dots represent molecular clouds in the Milky Way. And yeah, for others are from other 30 nearby galaxies. So we can say generally they follow a similar relation between the cloud mass and the star formation rate of the cloud. So I would think the molecular clouds in those nearby galaxies follow a similar star formation processes like those in the Milky Way. And the model developed for molecular clouds in the Milky Way are also applicable to molecular clouds in nearby galaxies. Yeah, okay, that's all. Thanks.
Thank you very much, gentlemen, for this talk. We have time for quite a bit of questions. Does anyone ask questions? If not, I'll start. I think I missed it, but could you remind me of how you derived the star formation rate here?
Star formation rate here is only from the middle infrared emission.